This is the screencast for section 7.3, example 3. We're going to look at washer cross sections. So as you saw in the rotation of an object or an area around an axis, sometimes that object, the solid object, will in fact have a hole in the middle. And that happens when the original area does not go all the way down to the axis of rotation. That creates a hole in the middle of the object. So still a solid object, but we're going to work with these type of cross sections that have a hole in the middle. We're going to call those washers. So example 3 says the region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine of x and y equals sine of x is revolved about the x-axis to form a solid. Find its volume. So here we have the two-dimensional y equals cosine of x, y equals sine of x. The intersection point there is pi over 4 comma square root 2 over 2. And we're going to revolve that around the x-axis. So over here you have a three-dimensional mock of what that would look like. Now as you can see by this pink ring here, our cross section, if we took a slice out of the middle of this object, the cross section would not be a solid circle anymore. It's a washer. So it's a circle with a hole in the middle. So the area of a washer is going to be pi times big radius squared, so the big area of the big circle minus the area of the little circle, the hole in the middle. Well, we got to find out what that big radius is and what that small radius is. So as you can see on the three-dimensional object, that big radius is determined by the top curve. So in this case, y equals cosine of x. The little radius then is determined by the small curve y equals sine of x, or the lower curve y equals sine of x. So on my washer, each cross section, the radius on the outside, the longer radius is cosine of x, the little radius is sine of x, if you're looking at the cross section straight on. So the area then is going to be pi big radius squared, so in this case cosine of x squared, minus pi little radius, or sine of x squared. So now we have the area of a cross section. Now we can stack all these cross sections up together and make this solid object. So we're going to find the value, and I'm going to integrate. I'm going to stack all of these cross sections together from 0 out to pi over 4. And here's the surface area of each cross section, depending on where we're at. That x value will tell me the exact area. And I'm going to give each one of them a little thickness with the dx. And now I can integrate with my calculator, and I got pi over 2 cubic units. The now try problem number 17 says find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So 17 is y equals x squared plus 1 and y equals x plus 3. So I graphed those in my calculator, and then the question is, how do I know what that's going to look like once it's revolved? Well, it's up to me to draw that picture. So a strategy that I have for drawing these pictures is once they're revolved around the x-axis, their profile is going to look the same above the x-axis and below the x-axis. It'll actually look like a reflection over the x-axis. So what I do is I take one part of the curve, so let's say the x squared plus 1 part, and I draw that on the opposite side of the x-axis. Then I'll take the other part of the curve, so the x plus 3 part, and draw that on the other side. Then I know that this is a revolution, so it's going to create a circular motion or circular shape. So I'll draw a circle connecting the two inside pieces and then a circle connecting the outside pieces, so you can kind of see what happens to each piece, and then there you can get that their cross section is going to be a washer. So now that we know that a cross section is going to be a washer, we need to find the area. So that's pi times big radius squared, so the whole big circle, minus the area of the little circle, pi little r squared. Well, from the drawing that we did, we can see that the outside radius, the big radius, is going to be determined by the x plus 3 graph. So that means r, capital R, is going to be x plus 3. Now the little radius is the distance between the x-axis and the inside curve, or the x squared plus 1 curve. So that means little r is going to be x squared plus 1. So the area of our cross section is going to be pi x plus 3 squared minus pi x squared plus 1 squared. So now that we know that what the area of a cross section looks like, we can take infinitely many cross sections, stack them on top of each other at different places on the x-axis, and get the volume of the solid object this is creating. So the volume is going to be integrated from -1 to 2. So I'm going to stack cross sections from -1 all the way out to 2 on the x-axis. And then I have my surface area of each of those cross sections, and then give them a little bit of thickness with a dx. Integrate, of course, with my calculator is how I did that, and I got 73.513 cubic units of volume.